group representative. Yes, it seems.
So, thank you everyone for coming. Welcome you to the research seminar today given by Jaroslav Merc, who is a visitor at the IAC and the postdoctoral fellow with the Czech Science Foundation from this October till 2020, end of 2026. He did his PhD in between Košice and the Charles University in Prague. Then he was a postdoctoral fellow at the Charles University in Prague, and afterwards a fellow at the ISO in Garching. And he's an expert in symbiotic binaries, a very peculiar sort of binaries. And we are very pleased to have him as a group here visiting us and working with us closely together. And today he will just give a brief overview about the mass transfer in those symbiotic binaries in the era of Gaia. And so I would give the word to Jaroslav.
Thank you very much. Thank you for giving me the opportunity, made me volunteer to give this talk. I will speak about symbiotic binaries in the era of Gaia, but actually this Gaia here is, you can replace that by any of your favorite groundbreaking mission, which is now ongoing. I will speak about TESS as well. And I will focus mostly on mass transfer and accretion, because these are the things I was working on in recent years. I guess I will give you more questions than answers, but anyway, I will try to talk about something interesting also for you. Some of you probably heard my talk last year on the seminar, so I will repeat something from that talk, because I would like to reintroduce symbiotic binaries to all of you to start at the same page. And basically, this is take away message about symbiotic binaries. So these are binaries. These are interacting binaries, and these are very wide binaries. So the orbital period of these binaries are typically in hundreds of days, up to tens of years. And the one component in a symbiotic binary, the donor, is a red giant, RGB or AGB star. And the accretor in symbiotic binary is more evolved star. It's a white dwarf in most of the cases, or a neutron star in some of the cases. There was a discussion in past in the community, and it's still kind of ongoing, if you would include red giant binaries with main sequence stars in this group, which I am a bit against, or black hole accrerators, or anyway. But in general, the community accepts the definition that symbiotic binaries are red giant binaries with white dwarfs or neutron stars. I'm always showing this sketch that I created years ago, but of course, this is a very simplified model of a symbiotic star. Symbiotic stars don't look like that in reality. They're much, much more complex. And I think that the best example I'm always showing, and now I have a new picture because this year it was released, is Aquari, which is a system which is one of the closest to us. So we can actually resolve the environment. For most of the cases on the pictures, symbiotic binaries just look like, a dot. So you cannot tell much from the visual point of view, but in Aquari you can. And this is a very new picture. I think it was from 2023, but released in October 2024. And the binary itself is there in the middle. And this, given that this is a very closed system, it's one of very few where you actually can see both stars. So this on the right is taken with VLT sphere instrument, which is for exoplanets, but thanks to the resolution, you can resolve really both stars in this case. So you see that the environment is very complex. We cannot get these images for all symbiotic stars because they are just far. But it's not only that the visually they are complex. This is a zoo of a spectra of symbiotic stars, optical spectra, and you see that they are quite complex. And especially it's not a super homogeneous group of objects. So what you have here is on that first panel, basically you have symbiotic stars, which we call shell burning, where you have a very hot and luminous white dwarf with a K giant donor or with M giant donor. So you see the molecular bands, which are typical for M giants. And you see plenty of emission lines, which are created in the nebula thanks to ionization from the hot component. Then you have a dusty type symbiotic stars, where you have a lot of dust. So basically in optical, you don't see much of a cool component, but you see a spectrum which looks like a spectrum of planetary nebulae. And that's actually, in past, many of symbiotic stars were incorrectly classified as planetary nebulae based on the optical spectrum. And only later when people looked in infrared, they found that, yeah, but there is a very luminous giant in there. So it's a symbiotic star. There is a small group of dusty symbiotic stars where you will not find the very evolved Myra donors, as in this case, but you will find a much hotter G-type giants, and these are called the prime type. But then you have also such symbiotic stars where you don't have very luminous hot component, and then the spectra are less rich in emission lines. And here I just show several types of this accreting only, what we call them, with white dwarf accretor. And you see these are with M giants. You see tiny emission in H alpha, but not much else. But as an example, this is not just true for accreting only, but it's just better visible. Not always we have just ordinary M or K type giants. We have S stars in some symbiotic stars, and you see that the continuum of the giant is a bit different. And we also have some with carbon giants. So then you see a bit different molecular bands. And as I said, we have also some with neutron star accretors, and those typically in optical are very hard to spot because they look like ordinary giants. And then in many cases of these accreting only symbiotic stars, you really need to go to UV or to X-rays to detect the symbiotic nature of an object, because in optical, it looks like an ordinary giant. It's much easier with shell burning ones because you have plenty of emission lines with high ionization potential, such that the giant itself cannot ionize. So you need something which is hot in there. If you want to fully comprehend the binary system, the symbiotic binary, you really need to do multi-wavelength analysis. That's because typically the giant will dominate in the optical and infrared. The nebula will dominate in mostly in optical. It's falling apart. Mostly in optical or in near UV, and the hot component is not contributing much in optical, but then it's dominating in ultraviolet or in X-rays. And in D types, dusty types, you have a lot of dust. So actually, you will have a contribution from a dust in near infrared or in infrared, and sometimes really hiding the cool component in the optical because of the extinction. So that was symbiotic stars are complex and heterogeneous. They're also dynamic, and I will get back to Era Quarry actually, because I really like this video, which was also released this year, which actually shows the evolution of the environment of Era Quarry over just a few years. I think the first is 2014, the last one is 2023, and you see how this nebular environment, which is creating the outburst of the Era Quarry, is evolving. So you really see that these are not static objects doing nothing in years. And you can see that dynamic environment also in the light curves, for example. So these are selected light curves of some symbiotic stars over 30 years. And you see that there is a lot of variability. Some is connected with the orbital motion. Some is connected with the mass transfer. You see outbursts in many cases. Then you can have the variability of both components. You have pulsations of a red giant, some variability connected with the hot component. So it's very complex. And of course, with these changes in brightness, changes in spectra are associated. So this is just an example of two spectra of two stars taken in quiescence and then in outbursts. And some emission lines are disappearing, some new are appearing. you have P Cygni profiles, and a lot of things going on with the spectrum. And another example is this one, connected with the variability, and it's Ares of Yuhi, symbiotic recurrent nova. I'm showing this one because we are all waiting for T Corona Borealis to finally decide to show us another outburst. So in Ares of Yuhi case, the recurrent time scale is a bit shorter. So you see here clearly two outbursts, and here you see the evolution of spectra. These numbers are in days, so you see how much the spectrum of a star changes during the outburst within basically less than a year. So they are very, very, very dynamic objects. The other thing is that depends on the time scale you're looking for, you will be seeing different things, of course. So symbiotics change on the time scales from minutes basically to decades. So for example, the flickering I will speak about later, or rotation of the hot component is on the order of minutes, but some orbitally related effect given the orbital periods are on the level of years or decades. Outbursts also can be ongoing from basically weeks to decades. The pulsations are somewhere in between. So you have a lot of things going on different time scales. And the other thing is that if you will just select one wavelength, you will have all this mixed together. If you have more wavelength that you study, you will start to be able to separate these things because they dominate a different wavelength. So for example, flickering and outbursts, which are connected with the hot component, will dominate more in blue, while the pulsations of the cool component will dominate in red because it is a red giant which dominates at that wavelength. And some of the orbitally related effect will dominate the reflection, for example, in blue, but ellipsoidal, which is connected with the orbital motion when the giant is filling the rotation, will dominate more in red because, again, that's the wavelength where the giant dominates. And I'm always saying that symbiotics are important, and everyone is saying that about object they study. But symbiotics are very interesting from point of view of studying many different astrophysical processes. That's one thing. You can study mass transfer, accretion, you can study jets, you can study winds, you can study dust formation, outbursts, chemical enrichment of the interstellar matter, and a lot of other things. And also they're quite interesting from the point of view of evolution of stars and binaries, because that's the stage which we still kind of don't understand well when the star interacts. But they were also proposed as supernova 1A progenitors. They seems to be important for understanding the magnetism among white dwarf binaries, to understand the close double white dwarf binaries, which is now seems to be important for gravitational waves detections, because with LISA we'll be able to see some kind of background which might come from white dwarf binaries merging and so on. So these objects are pretty interesting for other fields than just stellar interaction mass transfer part of the astrophysics. The main problem is that we are far from understanding these binaries. And I will try to address some of those. I can spend now the rest of the talk just saying what we don't understand, but it doesn't make sense probably. So I chose just two examples. One is that to illustrate that we don't understand symbiotics well. One of those is that we naturally ask the question how many we should expect. For example, when we talk about supernova 1A progenitors, yeah, but if you have 5, then they will not constitute a large fraction of the progenitors because they are just none of those stars to go to the outburst. So that's also a very natural question to ask. And people did that several times and came up with very different numbers. So this is, you see that it's basically beginning somewhere at 1,000 and then ending at 400,000 and something in between. I highlighted the paper I am authoring, but I think that we are slowly getting to this kind of number based on what we know, that we should expect tens of thousands of symbiotic binaries in the galaxy. The thing is that we currently know less than 300. So there is a huge discrepancy. The problem is that you need a lot of input physics in kind of population synthesis model to get those numbers. And apparently we're far from understanding that input physics. So then the output is, of course, questionable, let's say. And you can very well see that, because if you do population synthesis model, then you can evaluate the parameters of that population. And I just show, again, just two examples. This is the distribution of orbital periods of symbiotic stars. So in gray, that's observed orbital period distribution, and in red and blue, orange and blue, that's basically predicted distribution of orbital periods. These two models actually differ just with the formalism in common envelope evolution, which is also something we don't understand well. But what you basically see is that we should not expect symbiotic stars with orbital periods somewhere below like 1000 days, where we actually find most of them with these orbital periods. It doesn't seem to be kind of selection effect, because we now know orbital periods for most of known symbiotic stars, and there are a few, of course, with longer orbital periods. I'm not talking about D types, these dusty types, because they have Myra components, so they need to be very wide. So typically these are on tens of years. But this is a population of normal giant plus white dwarf symbiotic stars, and they are just there where we don't expect them. And the other plot I'm showing, because it just shows really very well the problem, is the mass ratios between the giants and the hot components. And actually, they are not exactly there where we expect them to be. So the problem is, the main problem, I think, is that we don't understand that stage when the binary components interact. Because, of course, at the beginning, these are two main sequence stars, and they are just boring because they just evolve without knowing about the other guy. But at some point, they will kind of interact. And this part is, of course, the most problematic one. There is something which is called common envelope evolution, and this is very important for symbiotic binaries, because either they need to somehow survive, not to end up as cataclysmic variables on the orbit of 2 days, because you have a red giant and the other star is already a white dwarf, so it was a red giant before, probably had to either fill the Roche lobe and start transferring the mass, or somehow survive. I will not talk much about the common envelope, because this is really something we don't understand much. But also something which is still lacking in the understanding is how really the mass is transferred in symbiotic binaries. And I will talk about that a bit more later. One of the questions was also the question of accretion disks that I will address as well. And magnetism, that's something which at any astrophysical object, someone will ask about magnetism. I'm not an expert on magnetism as well at all, but there were proposals on having magnetic white dwarfs in symbiotic binaries, and I will address that as well. So I will start now with some of the results we got in last basically 2 years, and I will start with the analysis of symbiotic stars with TESS data, because actually that's a work that started here at IAC last year when I was visiting IAC as an early career visitor from April to June, I think. And it actually ended up as this paper. So if you will be interested more, because I will not cover everything, then you can read this paper, which was published this year, at the beginning of this year. The main motivation was that basically test data were not studied for symbiotic stars, maybe just for a few selected objects, but not for a sample of symbiotic stars. So it can be interesting to explore this new data set, let's say. To cut the story short, the original idea was not to study flickering, because I was not expecting to see something like flickering with TESS, but we ended up studying flickering with TESS. So the flickering is the variability which is thought to be connected with the accretion disk around the hot component. given that TESS is observing in very red part of the spectrum, one would expect to see mostly the contribution from the giant. But apparently, with the precision of TESS, we can still study this kind of variability also in the red part of the spectrum. It's stochastic variability, so not periodic, on the time scale of few minutes to hours. As I said, given that it's connected with the hot component, the amplitude, this is what we know already from the ground-based observations, is rising towards blue. So highest will be somewhere in the near UV. From ground, we are limited to some, nowadays, to B filter observations, because if you will go more to red, you don't see anything. And in U filter, you are not much sensitive with modern CCDs. So basically, the ground-based studies are in B filter typically. What we also know about the flickering from few ground-based studies is that it's variable in time. It's connected with the accretion. So if this accretion will change, then the flickering, which is the signal from there, will change as well. And before we started this study, there were 22 sources with confirmed flickering among these 300 symbiotic stars. So not a huge fraction, but it's something which is not easy to detect. In contrast, for example, with cataclysmic variables, which are little cousins of symbiotic stars, where you have a red dwarf donor and white dwarf accretor. So the accretor is the same as in symbiotic stars, but the donor is different. These systems are much tinier. The donor is not contributing much. You don't have nebula, so you clearly see the signal from accretion disk. In symbiotics, you have so many other things that even if there is the accretion disk, the contribution to the flux you are observing is tiny. You cannot study accretion disk in emission lines, in contrast again with cataclysmic variables, because of course you have some emission from the disk, but it's completely outshined by the emission from the nebula, which is emitting in the same emission lines. So basically, you cannot see directly the disk in emission lines. So therefore, we just had 22 sources. This is how it looks with TESS. So this is one of the sectors where we had 20-second cadence for T Corona Borealis. It's showing flickering. This trend is real. With TESS, you have a lot of trends which are not real, but this one is real. So that's a long-term variability of T Corona Borealis. It's ellipsoidal variable. So basically, this is connected with the orbital motion. And there are three sections shown here. And you basically see that this is what we are actually looking for. This is the variability on the time scale of minutes or hours. And that's connected with the disk. This TESS data looks very promising for symbiotic stars because really you can study a lot of them. They fall in the TESS sectors. And this is just a histogram. We focus on the blue ones. These are confirmed symbiotic stars, not the gray ones, which are also include candidates. But you just see in each sector how many of the symbiotic stars are there. So pretty huge data set to work with. And that's also very interesting, but for some, we have more than one sector. So we can study exactly this variability in time because we have the sectors distributed over time. The other thing is that some of the symbiotics are just too faint. At the end, that was some work involved, but we ended up, I think, with the limit of magnitude 13 in TESS, because everything which was fainter than magnitude 13 was either dominated by noise or, it didn't make sense to do because the amplitude for such was lower than the length. But the main problem so these are pretty numbers, but the main problem is that not all symbiotic stars with TESS look like this one. This one is perfectly isolated, amazing target for huge TESS pixels. So if you are in the field like this, and this is not the worst example. So even in paper, I just didn't show the worst example because it was just a red square. So it didn't make sense to show a red square. If you are in this kind of field, it's just very hard to study stochastic variability. Of course, if you are interested in something periodic, let's say somehow, then you still can have confusion. But if you have stochastic variability, then you really need to care if that star moved out of your pixel or not. And if there are like 1,000 stars in the same pixel, then you need to be more careful. So this was the main limitation of the whole study, that for majority of symbiotic stars, actually, you were in the too crowded regions to study flickering. But at the end, we found that it is possible to study with limitations. We first focused on the 22 known flickering sources. 16 of them actually had usable light curves with TESS, and we detected flickering with TESS for 7 out of these 16. So we knew that we should see flickering in those sources because it was confirmed in the past. We detected for 7. It's not a problem at the end. It just says that the flickering is not always detected with the available precision of TESS within the TESS passband, because we are in very red, and at the time of observation. And that's also very important. And this is a very, very nice example of a star that had 5 sectors available. And actually, you see that in one of those sectors, there is no variability at all, while on the others, the flickering just turned on. This is not just observed by TESS. This is actually confirmed by ground-based observations, X-ray observations. So we know that this is real. So that star was showing very undetectable flickering at some point because the accretion rate was very low. Then the accretion rate increased, and the star started to show much more prominent flickering. So at the end, it's not unexpected result that we didn't found flickering for all of the known flickering sources. More interesting is that actually we found from 72 studies that were within the magnitude range and not in crowded regions. So we then focused on all other symbiotic stars, but we had to limit ourselves to those that had usable light curves. So for 72, which we studied, we found 13 new flickering sources. And here is basically the one of the main plots. What you have in blue is basically the comparison sample of single red giants. So those are supposed not to show anything. Of course, there will be kind of variability detected because you are detecting noise, and it's somehow rising, of course, with the for the fainter sources. And if the symbiotic stars fall in that region, typically it's because the light curve is dominated by noise. But in some cases, you see much more prominent variability, and that's actually what we were looking for. So we detected 13 new. So 13 plus 22 is 35. So it makes now 12% of the known symbiotic stars. So we have flickering detection for 12% of symbiotic stars. Pretty small fraction, but actually it's very interesting results from that point of view, that now we have detection for more than 80% known accreting only symbiotic stars. These accreting only have low luminous white dwarfs or neutron stars. So you don't have much of the contribution from the nebula. So there should be, in principle, no difference in accretion disks between shell burning and accreting only. It's only that in accreting only, it's much easier to see the variability from the accretion disk because you don't have a strong contribution from the nebula. And if there is no difference, then you can generalize this conclusion to fact that accretion disk seems to be very common in symbiotic stars. It's hard to study them. It's hard to detect them for shell burning ones, but not because they are not there. It's just because it's observationally very difficult. So, but that is one of the actually unexpected conclusions from analysis of this data of symbiotic stars. And as a side result, that was completely a side result of the analysis of test data, and in the paper is just mentioned very briefly because that's the follow-up work we now do, is the magnetism of the white dwarfs in symbiotic stars. This whole field in symbiotic stars was motivated by the detection of the periodic variability with the period of 28 minutes in 1999 in Z Andromeda, in one of the prototypes of classical symbiotic stars. So they detected this variability in blue with this period and claimed that it's because of the rotation of the magnetic white dwarf. You can read the paper. They also consider some other options like pulsations of the white dwarf and so on, but they For example, they said that with G multiplications, it would be multi-periodic. It would change on the time scale of a few months. They were observing for a year, and there was no change in the period. So they then proposed the explanation for this period, that you have a magnetic white dwarf in this symbiotic binary. Since then, there were a few other systems with similar periods detected. We added, as a really side product of our work, we added 2 more. Because if you are studying, test data, you will see that the periodic variability on those timescales. So here are the periodograms. With this first one, I am pretty sure that this variability is connected with that object, but we would like to confirm that. So we submitted a proposal for IAC time to confirm it's accepted. So we will see soon if this is really variability connected with the correct object because of the test pixels. In the second case, I'm not sure. So you will, if you are more interested into that, you can check the paper on flickering, because we speak more about that. But in that case, I'm not really sure about which object actually this variability is coming from, and it was just impossible with test data to say something more. But with the first one, I'm pretty sure. But the most interesting actually result of this was that, so I forget that. I want to first say why it's actually interesting to bother. It's because there are several points why this is interesting. There is a very recent paper where Diego Belloni and colleagues studied evolution of symbiotic stars with magnetic white dwarfs. In particular, that was a test case for them. First of all, they found that there should be more magnetic symbiotic stars. So they're waiting for us to be discovered. But very important result was that it seems from their modeling that symbiotic interaction is necessary for understanding close white dwarf binaries with one magnetic component. That these stars had to pass through symbiotic interaction in past. The other thing is that this detection of rotation of a magnetic white dwarf presented by Jennifer Sokolowski in 1999 was then used as a very important piece of evidence in an effort to explain the outbursts of classical symbiotic stars. Because symbiotic novae, as RS of Yuki or T Corona Borealis, or those which we call slow symbiotic novae, that's a thermonuclear runaway. So we understand the physics. With majority of symbiotic stars is showing different type of outbursts, and we don't know exactly what is the physics. And one of the proposed explanations was that it is kind of thermonuclear runaway, which is started by an accretion event in the disk. They call that combination nova. So it's kind of combination of dwarf novae and classical novae. And for this theory to work, we should explain the variability of Z Andromeda, this 28-minute periodicity, as rotation of a white. And now our result. So they observed Z Andromeda in 1997. This is the period they obtained, 28 minutes. We analyzed the test data, which were taken 25 years later. The period changed. It changed by 80 seconds in 25 years. We don't have anything in between. So we cannot tell if that was a gradual change or if that was an abrupt change, or what was the reason for that. If that is gradual, it should be like 4 seconds per year, which is quite a lot. The important thing to show is that their observations were taken at the very beginning of a very long active stage. There are plenty of outbursts of Z Andromeda detected in the meantime, with outflows detected, some kind of jets. So that could play a role in that. Yeah, works. Test observations that we published were obtained in quiescence already. So now, I spoke with Jennifer about this. I'm not a theorist, so I am observer. So for me, I see the 80-second change. Now it's up to theorists to explain the change. But we spoke with Jennifer, and it seems that it's very hard to explain 80-second change if that is a rotation of a white dwarf. So first of all, we don't have anything in between, so it's hard to tell. So what we want to do is now to follow up the system to see if it continues to change, or if that is something which is connected with the outbursts. I would expect that not to change, because we are already in quiescence, so there are no more outbursts since test observations. So we should retrieve test value, right? So let us see. But this would be very important test case, because if that is something else, then this can be something else also in the other symbiotic stars. So at the end, we maybe have no magnetic white dwarfs in symbiotic stars. It's just the variability connected with some other phenomenon. And in the rest of the talk, I will focus on mass transfer, because that's what I promised as well in the at the beginning. Because we still don't know how the mass is transferred in symbiotic binaries from the donor to the accretor. It can be rho slope overflow, so the giant is filling the rho slope, and we have the mass transfer. But given that we have a red giant, in contrast with CVs, where you have a boring red dwarf that needs to fill the rho slope to transfer the mass, we can transfer mass via wind quite effectively. And it works because we have long period symbiotic systems and D-type symbiotic stars. So if you have an orbital period of 500 years, it's just hard to fill the rho slope, right? So it's transferred via wind. So we know that this is a possibility. But the thing is that what is the dominant mechanism, especially in the short period symbiotic stars? It can also be some kind of combination that was proposed, like wind rho slope overflow. So it's not the giant that is filling the rho slope, but it's a wind which is then focused towards the companion. The problem is that when people asked this question in past, they, for example, obtained the radii from rotational velocities, assuming synchronized rotation, or from spectral types, assuming luminosity class 3, because we have giants. I will tell you something a bit later. So from those radii that people obtained for the red giant, it seemed that they are not close to filling their rho slope. So the main mass transfer mechanism would be the wind, and we are all happy. The problem is that later, people obtain light curves in infrared. You don't see that in optical, because the optical is dominated mostly by the nebula. But if you go to infrared, you start seeing quite a large fraction of symbiotic stars showing ellipsoidal variability. So that's a variability with the half of the orbital period, because the giant is filling the rho slope, so it's deformed, tidal deformed. And when you see it from the side in the quadrature, then you have more light than in conjunction, right? So then the main mass transfer mechanism should be the rho slope overflow, because we see the large fraction of symbiotic stars with this variability. People claimed, and I'm working on interferometry, so that interferometry is the most straightforward test to do that. We will observe the star, we'll see how big it is, and we will, evaluate the mass transfer mechanism. Up to now, actually, there were just 4 symbiotic stars observed. It was in 2014. The paper was published in 2014. And this is basically how I try to represent the result of that. So for 3 stars, we have some lower limit on luminosities. For 1, we have, somewhere, but with this huge uncertainty. Because at that point, we're just able to guess a distance to that star, but not really do something. Now we have Gaia, therefore I put Gaia in the title of the talk. Yeah. So now we have Gaia. So something we want to do is to use that to get a bit more precise picture of symbiotic stars. Something like that. That's a kind of prediction. This is not observed, but that's because we are still obtaining data. So I have accepted proposals on the LTI and Chara for observations of more symbiotic stars, because we took, the list and we tried to observe everything what makes sense. Most of symbiotics are far, so the giants will be small, so we will not resolve anything. But about 10% of the giants can be resolved. So then you can measure the angular diameter, and from that, somehow, you can get the radius. So it's simple. It sounds simple. It's not. But the idea is that you have angular diameter, then you have a distance, so you have a linear radius, and with, again, some steps in between, you can read in the paper, which will be submitted soon, we can get the Rho-Shell filling factor. So this is just an example of the model, because for most of the stars, we don't see any deformation, so it's a spherical star, and this is in the red, it's a fit to black observed data for this particular object. So in this first paper, we studied 6 individual stars. 3 of them are, yeah, fine. So the Rho-Shell filling factors are relatively small, but it's fine because we don't see ellipsoidal variability, and interferometry is saying us that they will not be filling the Rho-Shell. So more or less fine. There are a few lessons learned already from this exercise. First of all, that you cannot estimate the radius and luminosity or the distance or whatever, assuming class 3, because I don't know why people do that. The evolution in that part of HR diagram is basically perpendicular, right? So that star, of course, will be at the luminosity of class 3 at some point, but then we'll just evolve more and will go away. So we'll be bigger, more luminous, and the distance, if you will assume luminosity class 3, can be underestimated and so on. We see that. It also seems that the assumption of synchronized rotation might not be valid. So you cannot obtain your radius assuming that the rotation of the giant is synchronized with the orbital period, because it should not could not be always. And very important thing that we found was that you don't see the white dwarf in the spectra. So if you want to have a mass ratio, you can use just an indirect way how to do that. And people use helium-2 emission lines because it seems that they are formed close in the nebula to the white dwarf. So then you measure the variability of helium-2 lines, then you have a giant, then you have a mass ratio. But it seems in all the cases where people did that, the mass ratio is overestimated by a factor of 1.5, 2. So you are getting incorrect mass ratios. The fourth star in the sample was this one in Pavonis, which seems to fill the Rho-Shell or be close to filling the Rho-Shell. And there is a hint of ellipsoidal variability in the light source. So this one is also fine. We see ellipsoidal variability. It seems to fill the Rho-Shell fine. These one are the troublemakers, these two, because you see that the Rho-Shell filling factors are pretty low. So like half of the Rho-Shell. So we would not expect to see ellipsoidal variability. But what we see is actually ellipsoidal variability. But from interferometry, we cannot retrieve the Rho-Shell filling factors, which are big enough to explain the ellipsoidal variability. So these are the light curves, and you clearly see that there is variability of half of the orbital period, explained as a consequence of tidally deformed giant, but it should not be tidally deformed because it's just not big enough to get to the size of its Rho-Shell. And here is actually the comparison of the blue is how it should look like if the giant is filling the Rho-Shell. This is what we observe. So it's not that we just, wrongly fit the data. It's really the difference is quite large. So now, okay, how to make them fill the Rho-Shells if it is a Rho-Shell overflow? Yeah, we are using Gaia. So the distance can be underestimated. And you see that in this first case, the Gaia DR3 distance is 382 parsecs, but the Ruve and goodness of it is like huge. To fill this star, to fill the Rho-Shell, we need to take it and to put it in the distance of 700 parsecs. In the second one, it's even not that bad, but the difference is even smaller. So, okay, that's a natural explanation. Yeah, distance is underestimated. We are all happy because if you just move the star for the same angular distance, you will get angular diameter, you will just get a larger diameter. So we try to test that. Because the main problem with symbiotic binaries and many other binaries with Gaia is that they are binaries. So this is how the track of this particular star would look like on the sky if that is not a binary. So you see something which is due to parallax motion. And if you fit this with single star model, you will get the correct parallax, right? But the thing is that if you have a binary, your astrometric track will not look the same. So the green and orange or the reddish one are the same star at some distance, the same distance as the black one, but with binary motion added. And you see that the track, it looks not that ideal. But what is done then for obtaining the astrometric results, astrometric solution, is that you fit this binary system with a single star model. Because for symbiotics, it's always the single star solution in the RT. So then the question was that, okay, we know that we are not doing that correctly, but can the binary motion be accounted for this difference? So this is what Gaia is observing. This is what it should see at the distance where the giant would fill the Jaroslav. So let's assume that the star is at that distance, and it's just because of we are using single star solution for binary star that we are obtaining the wrong parallax here. So we simulated this 100,000 times with different orbital orientations, but with the period of that star at the position on the sky of the star. That's important for the scanning law. So we adopted Gaia DR3 scanning law, the actual one. And no, if you are really at that distance, yes, you will get some scatter depending on the orientation of the orbit, but not that big to get from here to this value. So the binarity apparently cannot be the only problem here. For the second one, the distances where the star would fill the Jaroslav are closer. So for that one, it works. So that, okay, let's say that in that case, the distance is underestimated and it's fine. So to have an idea what we can expect for symbiotic-like population, what we did was to simulate the population of binaries to see how much binarity is influencing the astrometry. It's actually the same approach that was already done before, and we used the code of the outers, but what we did is not a general population of binaries, but we simulated those with parameters like symbiotic stars. Because we have some mass ratio, we have some light ratio, so that would make you the motion of the center of light somehow constrained for you. And also very important was that we adopted the actual Gaia DR3 law. They just simulated DR2 with randomly sampled data. So that work is very nice to understand how much binarity is influencing the astrometry. But if you want to say something about your particular sample, you need to repeat that with the parameters of that sample. And what we found is, of course, if you have a period of 1 year, your astrometry can be very much influenced. This is the density. It's not always very much influenced, but it can be. This is the absolute difference. So you can have a very large difference in absolute values between the actual and fitted parallax. And here, what you see is that, of course, that difference will be smaller if you are further away in absolute values. So therefore, I decided that it might be more interesting to see like a factor of difference. So this is fitted parallax divided by the observed parallax. So for many systems, it's actually okay. So depending on the orientation of the orbit, you would get close to the right value, but it can be off by a factor of 2 sometimes. And this factor of 2.5 or 1.5 doesn't depend on where the star is. So this is the value to keep in mind. But it will depend on the orbital period. So it will be the parallax will be more affected for shorter orbital periods, because for the very long orbital periods in the R3 you have just 1,000 days. So if you would have the orbital period of 5,000 days, you will just add something, but not additional sine wave. It can very much influence the proper motions. That's one of the other conclusions. But from this exercise, again, if you will be interested in more, it will be in the paper. it doesn't seem that we can explain this by underestimated distance in case of the one in Orionis. Maybe in the case in the second case, yes. But if we will even say that all these stars are filling the rho slopes, we will have the major problem with the mass transfer stability, because the mass ratios, if we will assume that they are filling the rho slopes, will not allow stable mass transfer. So then we see all the symbiotics that are filling the rho slopes in the very short stage just before the common error, and they all will just disappear, which is a bit improbable that we just catch all of them in this very short stage of life. So then there are other possibilities. For example, that it's a wind filling the rho slope, and that is causing the ellipsoidal variability, but the giant itself is well contained within the rho slope, or that we are just calculating the rho slope wrong way, because we all use Eggleton's formula, but that might not be valid always for a pulsating star with a strong wind. And there is a work you can also check that actually claims that the rho slope size can be reduced by a factor of 2 for this kind of stars very easily. So that means that the giant will be smaller than what you will predict from the Eggleton's formula, but actually will fill the rho slope, so will be tidally deformed. But then you can get cannot use the formula to get the radii for those that are filling the rho slope. And this is actually possible to test. And the one in Orionis is a perfect test, because we see the ellipsoidal variability, rho slope filling factor is 0.5, and it's pretty big on the sky. So this is the size we measured from the interferometric observations. So we should see the tidal deformation with VLTI Pioneer easily if we will observe at the right moment at the quadratron. And I am sure about this because last week my paper was accepted, where I showed for the first time that we can actually see the deformation of a red giant in a binary with interferometric observations. And that star is like a factor of it's half of the size. And we were able to see the deformation. So for the one in Orionis, we should see that if we will observe at the quadrant. So it's really a good test for this kind of question. So I will just sum up in 3 points. Accretion disks, common. Magnetic white dwarfs, maybe, maybe not. Rho slope overflow, maybe, but we have a lot of problems. So this is something to study observationally and theoretically as well. And with that, I will end. Thank you very much.
Who's in the room? No, people want coffee. I can ask you one. I may have asked you this already, actually. I'm going back to your period problem, so to your review of symbiotics. As you know, I work on previous stages of interactions, and some of my objects could lead to some of your objects. And I wonder if you have a guess or an estimation of how much of your period problem is because of the symbiotic phenomena, or is inherited from the previous stage of interaction when the white dwarf was an AGB star?
I have no idea. Yeah, but that's something what we spoke yesterday evening as well. But this should be put into that picture. But I think that a lot of that would come from the previous stages, not just from the symbiotic phenomenon, because very much the orbital periods for symbiotics will be influenced by how you treat that common envelope, avoiding the common envelope, or these things. So yeah, if you will just have a rho slope overflow in this first stage of interaction, where the current white dwarf is a red giant, you should end up with shorter periods. So then something had to happen there, not to get to that point of CV with few days orbit. The other thing is that we simulate the population based on the physics of the current mass transfer, because you need to have the mass transfer there to create the observational phenomenon, which is a cut in the simulations. Yeah, so it's not a red giant white dwarf binary random, but it's a interacting one. So you include winds, you include rho slope overflow or whatever, and then okay, this is a symbiotic star, this is not. This is just a random red giant white dwarf binary. but if you don't include, for example, the wind Roche bubble flow or this kind of things, then you are again just stick to these two possible channels: the Roche bubble flow, which you're just somewhere, you know, going to short periods, or the wind, which is going to longer periods, but not where you are.
I don't know if someone thought of a question in this time. Yeah, but then they won't hear you in Zoom, so let's just.
Thank you. Very, very nice talk. I was interested in flickering, in the flickering that you showed in the beginning. And I was wondering, what is our progress in the photometric modeling of this? So can this be modeled somehow? And
Yeah, you can get some information from like, yeah, modeling, because it seems that it's some kind of disturbance in the accretion disk. And the good thing is that it is not observed only for symbiotic stars. This kind of thing is observed in all accreting systems. And it seems that the properties can be linked to the type of the accretor. So there is I don't remember the year, but it's pretty recent work where they put this into the context of black hole accrerators, neutron star accrerators, white dwarf accrerators in symbiotic stars or cataclysmic variables, because the accretor is the same. And it seems that you can learn something from the behavior of the flickering about the accretor. In symbiotics, the main problem is that the donor is just, you know, yeah, maybe died.
thank you.
Anything else? Notice 1:30, no, 11:30, we can go for coffee.
But it's more a question on theoreticians. So I observe it. It's for other people to model.
So yeah, we can thank Jaroslav again and go for a coffee.
So I guess I can stop it here as well, right?